Okay, good afternoon, everyone. Welcome to today's online session of the Midas Elite Center. Today we'll be hosting Session 7, the application of slope stability and numerical analysis in the design process of dams. Okay, so all of our materials are copyrighted, so please make sure to receive our permission before sharing these materials in any type of lecture format. Okay, so here are today's learning objectives. So at the end of this course, we'd like all participants to gain an understanding of the theoretical principles of the limit equilibrium method and the strength reduction method of slope stability analysis. So those are the two main methods used for slope stability analysis, and we want everyone to gain an understanding of the theoretical principles that drive them. And also we want all participants to understand the key differences and unique advantages of each analysis method. So sort of what makes each method unique and what sort of conditions would make one method preferable over another. And last, we will go over the seepage and slope stability analysis applications for dam design. So how slope stability analysis is used specifically for dam designs and embankment design. Okay, so here is the table of contents, or the index, for today's lecture. So first we'll go over just the basic background of slope stability analysis, or slope stability applications. Then we'll go over the theoretical principles of the limit equilibrium method as well as the strength reduction method, and we'll include a direct comparison of the two methods. And last, we'll go over the how slope stability analysis is used specifically in dam design, and we'll go over sort of specific applications of seepage analysis and how it's linked to slope stability. Okay, so first, chapter 1, we'll just go over briefly just the basics of slope stability. Okay, so why exactly do we need slope stability analysis? So typically it's used to analyze the safety of natural and man-made slopes. So the main design objectives of slope stability include the following. So we want to find endangered areas, so areas that might be compromised or that might be in danger due to the possible failure of a slope. The investigation of potential failure mechanisms. So we would like to predict accurately how the slope would fail and what sort of would cause it to fail. The design of optimal slopes with regard to safety, reliability, and economics. So with man-made slopes, we want to design slopes to be safe, to be reliable, and also to be cost-effective. And the design of remedial measures such as barriers and stabilization. So sometimes when slopes aren't stable enough on their own, will include, or engineers will design for specific structural supports that will keep that slope stable under certain conditions. And before I move forward, I just want to talk about this picture a little bit here. So here we can see sort of the way a slope typically tends to fail. So as you can see, there's a failure surface and sort of a rotational type movement where the slope will start to slide down the sort of the embankment here. Okay, so successful design of the slope requires the following data. So first we need the properties of the soil and the rock mass, slope geometry, so just basic geometry of your project site and slope. Next, your groundwater conditions. So groundwater conditions, or to be more precise, poor water pressure has a very strong effect on the stability of a slope, and we'll discuss that in greater detail in the fourth section of this lecture. Next, alternation of materials by faulting. So for example, you'd like to know if your material is uniform throughout the slope, or if there is maybe a certain fault line or cracks in the slope where material changes. These can lead to sort of shear stresses or shear forces that could really affect how stable your slope is. Joint or discontinuity system. So once again, you want to see sort of how the soil strata differs along the sort of length of your slope. Because different soils have different sort of properties, and those properties react differently to shear stressing, thus affecting the stability of your slope overall. And then movement and tension in joints. So for example, if you have any sort of support structures, if you wanted to double check the movement and the tension in those structures to ensure that it can withstand sort of the forces acting down upon it, and that it can securely stabilize your slope. And last but not least, earthquake activity. So that's pretty self-explanatory. Obviously, if there's seismic loading being applied to your slope, a certain sort of amount of seismic loading can cause it to fail. Okay, so here are design applications of slope stability now. So first and foremost, we'll talk about embankments, and we know once again we'll discuss these in great detail in the fourth section. But just to sort of get you introduced to sort of the main sort of pieces or the main elements of an embankment. Typically, you'll have, it'll be sloped. Your embankment will be sloped on both sides. There'll be a side that contains the water, also known as the reservoir. That's also known as your upstream area, as opposed to your downstream area, which is your dry side. And then also, because of seepage, typically many of these embankments have a clay core to sort of to stop the seepage, as well as a drainage blanket to sort of carry the water away from this slope here, which could be compromised due to seepage. But once again, we'll go into greater detail about embankments and slope stability design for embankments in the fourth section. But this is just a basic introduction of design applications for slopes. So embankments, absolutely are typically, or slopes especially, are used in the sort of the design process of embankments, especially earth embankments. Okay, then also road cuts. So as you can see, typically when a road is being built or constructed, sometimes slopes need to be sort of constructed to the side of those roads to make room for them. So as you can see, sometimes engineers determine that these slopes are stable enough to sort of stand on their own, but there are other times when slopes are steeper, when certain man-made reinforcements need to be included as well. Another thing to take note of is that in certain road cuts, engineers leave a certain amount of area here just in case there's any sort of a slippage or any sort of degree of slope failure. So that way, when there is any sort of failure, any sort of debris won't go directly onto the road, but rather onto this sort of designated area here. Okay, then open pit mines. So open pit mines or open cast mining is a surface mining technique of extracting rock or minerals from the earth by removal from an open pit or burrow. So as you can see, open pit mines are dug on benches, which describe the vertical levels of the hole. These benches are usually 4 to 60 meter intervals, and depending on the size of the machinery that is being used, will sort of determine the sort of the length or the width of these intervals. So most walls of the pit are generally dug on an angle less than vertical to prevent and minimize damage and danger from rock falls. So this depends on how weathered the rocks are and the type of rock, and also how many structural weaknesses occur within the rocks. So as you can see, because typically these are sort of excavated along rock lines, or rock layers, there isn't too much need for structural supports. But because we wouldn't want any sort of failure to occur, it's always a very good rule of thumb to check for the stability of these various slopes. And also to check for structural weaknesses within the rock, such as faults, shears, joints, or like sort of foliations. So those are important things to consider when constructing these open pit mines. But there are some instances where additional ground supports are required, such as rock bolts, cable bolts, and shotcrete. And also dewatering bores may be used to relieve water pressure by drilling horizontally sort of into these walls, which is often enough to cause failures in the wall by itself. So even though rock slopes are naturally much more stable than soil slopes, there's still various things to consider, and there still are instances when sort of structural reinforcements might be needed, especially for open pit mines, which consists of several layers of slopes. And then naturally deep excavations. So as you can see, whenever sort of excavations for foundations are created, slopes are just sort of a natural part of an occurrence of creating these foundations. So until these foundations are built, the stability of these slopes need to be checked, to be designed for. Oftentimes there are tiebacks or soil nails that are sort of enforced into these slopes to support them. But depending on the type of soil, so to the soil to the left here is actually very clay soil. So as you can see, it can sort of stand very firm on its own as long as it's not sort of too high. So that's another important design consideration, is the type of soil that you're excavating into. And then last but not least, landfills. So as landfills are essentially just these large openings. Oftentimes open pit mines are converted into landfills. And what they'll do is they'll take these huge openings and they'll fill them with debris or with waste. But until these landfills are completely filled up, our engineers would like to check the stability of these slopes that sort of surround the landfills, just to ensure that because you don't want any sort of failure to happen. Otherwise, the landfills can sort of fill up, and that sort of defeats the purpose of having them. So sometimes, as you can see, engineers will include or import certain structural reinforcements to keep these slopes more stable. And as you can see, man-made slopes, they'll often use sort of larger equipment to create these slopes. Okay, so that was just the first part. Now we'll have a quick quiz. It's the quiz comprises of 3 questions, multiple choice. You'll have up to 5 minutes to finish. So please just take your time, and once you're done, just hit the submit button and we can move forward. Okay, so I see everyone has submitted their quizzes in on time. So now we'll just move forward. So now we'll move to Chapter 2, which will discuss the limit equilibrium method. And we'll go over the development history, theoretical principles, certain analysis considerations, things you need to take into account when using the limit equilibrium method, and we'll also go over how it specifically applies to dams and embankments. So first, just the development history. So the limit equilibrium, it is the oldest and most well-known technique for slope design. So it's been around the longest. It's the most widely recognized. It's the most widely used. And it utilizes something called the method of slices. So essentially what the method of slices is engineers will take the slope and will divide it into sort of several slices, and they'll analyze the forces acting on those slices that are sort of keeping them in equilibrium. And then, based on certain, equations that have been developed, they'll take these forces and they'll determine sort of the critical sort of failure surface or the critical point, or to determine the minimum factor of safety. So initially, interslice forces were ignored. So interslice forces are the forces acting between the slices themselves. This was done to sort of simplify things, and also because sort of equations hadn't been developed, or the equations hadn't been quite developed to really take those into account effectively. So those were ignored. Certain assumptions were made in order to sort of, not necessarily account for interslice forces, but to overcome having to, calculate them. And thus an iterative approach became necessary. It's sort of a trial and error. Engineers would have to create several sort of slip surfaces or several curves. They'd have to analyze the forces on the slices one by one until they found sort of their minimum factor of safety. So it was a very sort of long and tedious process up until certain advancements were made that really sort of expedited this limit equilibrium method. Okay, so in the 1950s, Bishop and Yanbu considered interslice normal forces. Then these were called the Bishop simplified method and the Yanbu simplified method. So if you look to the sort of the bottom portion of your screen here, as you can see, this just sort of goes over the different methods that are available. And as you can see, the Bishop simplified method, directly takes into account the normal interslice forces. And then in the 1960s, computers made it possible to streamline iterative procedures. So therefore, mathematically more rigorous formulations were then possible. So two sort of prime examples of this are the Spencer and the Morgenstern-Price methods, which include both interslice normal and interslice shear forces. So as you can see, the Spencer's and the Morgenstern-Price method not only consider the normal forces of the interslice forces, but also shear forces, or sort of forces that are acting up and down between the slices. So this is harder to do. It's more mathematically sort of rigorous, but because of computer programs, engineers were able to sort of utilize these methods to get more accurate results, or more detailed results as far as their limit equilibrium methods. Okay, and then moving on, in the 1980s, desktop computers made it possible to develop commercial software packages that were based on LEM formulations. So some of these software packages include SlopeW, Slide, Stable, and then SoilWorks. So it's a safe assumption that any sort of geotechnical firm that's out there has some form of LEM software. It's very it's very efficient. It's very easy to use. And then just using these programs, they can easily calculate, multiple sort of arc surfaces or slip surfaces. They can, automatically compute all the, forces that are acting on each slice. And most programs will actually isolate your minimum factor of safety for you. So it's very convenient. So something that's sort of lost with all these computer programs is that, a lot of engineers really don't understand the theory behind the limit equilibrium method. They know that it works, but they're not really sure how it works. So I guess that would be a good benefit of just this lecture in general, is to understand how these computer programs are coming up with these solutions. Okay, so to go more into detail about the method of slices. So first, it's based solely on statics. So because it's based solely on statics, what we're assuming is that all the slices are currently in equilibrium. So because the forces are in equilibrium, the forces act on each free body or on each slice such that it will remain stationary, and therefore all the forces, as well as the moments, should add up to 0. And then the resulting computed forces may not represent the actual field conditions. So that's another important thing to keep in mind, is that if, say, for example, you check your slices, or you check the forces acting on those slices, just keep in mind that there are various assumptions that are taken into account or that are made when doing the limit equilibrium method, which would sort of lead to forces that may seem erroneously high or erroneously low. And just keep in mind that those don't actually represent, actual forces in the field. Those are just the forces that are, being used to assume equilibrium. So just because you have forces that are computed that may not seem to actually, represent those field conditions, that doesn't necessarily mean that your factor of safety is incorrect, or that your that the results that you are getting for the factor of safety are erroneous as well. So it's based on two factor of safety equations. The factor of safety with respect to the moment and horizontal force equilibrium, and as was first published by Spencer in Geotechnique. So the main, as far as the Spencer-Morgenstern, Spencer's method, it's based on these two factor of safety equations. And currently the Spencer's or the Morgenstern-Price method are really the main ones that are used today, that are implemented in those computer programs we mentioned previously. Okay, so I won't go into too much detail just about all the forces acting on the slices, but just keep in mind that the program takes all these forces into account when calculating your factor of safety. So for example, the normal force, or excuse me, the weight of the slice itself, the normal force acting back upon it, shear forces on the bottom of the arc, as well as interslice forces both in the normal and the shear direction, and as well as sort of any external forces acting down upon the slice itself. So those are just, it's another important thing to keep in mind, and you can refer to this later on, maybe when you're studying in your own time, just all the different forces that are being applied to your slice. So as you can imagine, to do this by hand would have been a very long and iterative process, because you have to calculate these forces for each and every single slice, and then you have to take those calculated forces and then apply them to a factor of safety equation, which I'll show you momentarily. So hopefully this gives you a better appreciation of what these programs do for you, as they take a process that was very long and iterative, and they compute it automatically for you, so that you can focus more just upon the input and then the results, as opposed to the actual process of having to do the calculations. Okay, so here are the factor of safety equations. So the two factors of safety that are determined are the factor of safety for the moment and then the factor of safety for the force. So these are somewhat self-explanatory. I won't go into too much detail, but just keep in mind that the normal force is used in both the numerator and the denominator of each equation. So it's very important that the normal force is calculated correctly for each slice. And just as a recap, I'm sure you're all familiar with what the factor of safety is, but just to reiterate, the factor of safety is essentially just a ratio of the forces that are keeping the slope stable versus the forces that are acting against the slope, that are pushing up against the slope to maybe cause it to fail. So usually a minimum factor of safety for most cases would be about 1.5. So in other words, for every say you have maybe 1 Newton of force acting against the slope, causing it to be unstable, proportionately you'd have 1.5 newtons of force acting against it to keep it stable. So the higher your factor of safety it is, the more stable your slope is. Okay, so now let's go over just how to sort of decide upon your slip surface shape. So with most programs that are out there, they'll allow you to select or to create your own sort of arc failure shape. So here's just a sample of a circular arc failure shape. So as you can see, it takes a sort of a circular curve here, and then depending on how many slices you want to create, that usually that's user defined. What it'll do is it'll take a circular failure surface and it'll create the slices. But some important things to note about circular failure shapes. First and foremost, that if you look to the graph on the right here, as you can see, the factor of safety, as far as interslice shear is concerned, interslice shear affects the force of the of your slope, but it doesn't affect your moment. So why is that? So just imagine, if you will, this curved portion here as just like a solid piece, or a solid piece, like a solid block, a solid circular block. And say, for example, you were to apply a moment force upon it. As you can imagine, there wouldn't really be much resistance because of its shape. It would just simply slide up. That's why the interslice shear doesn't really affect the moment. So as you can see, as the interslice shear increases, the moment just stays the same. So just imagine adding greater and greater amounts of sort of rotational force upon it. There wouldn't be really any resistance at all, except from maybe some shear at the bottom. That in this case would be taken as negligible. Whereas if you were to take a horizontal force, so say you're to apply it sideways or laterally in this way, you would get some interslice, or you get some resistance, because just of the way that the slip surface is oriented. So that's why, as you can see, as interslice shear increases, the force on the factor of safety increases as well. So that's another important thing to keep in mind. So depending on the type of forces that you see acting on your slope, a circular arc failure surface may or may not be ideal for you. So if you're expecting little to no sort of rotational force acting on your slope, then a circular failure surface might be your best bet. And so, because you'd only really need to account for the sort of the shear force or the lateral force. Whereas if you were affecting maybe a significant amount of rotational force, then this sort of circular arc failure surface would not be as efficient for you, because you wouldn't be able to account for it. So let's take a look at another type of shape here. So now let's take a look at the planar slip surface. So once again, the main difference between the previous, or the arc failure surface, and the planar slip surface is just the shape of the surface itself. So as you can see, instead of a rounded shape, now it's just a straight line going from one point of the slope to another sort of point up here. So now the case has been reversed. So as you can see, as interslice shear increases, it's the moment that changes, but it's the force that stays the same. So now, once again, just try to imagine this sort of arc failure, this failure surface here, as just one solid piece. And let's say, for example, you were to apply some, normal force upon it, just going in, sort of the perpendicular to the slope itself. As you can imagine, the entire piece would just slide, just along that top surface here. I mean, you'd get some resistance just along the bottom, but once again, this is just sort of taken as negligible. Whereas if you were to apply a rotational force this time on this sort of piece, you get some resistance. So if you were to apply, a rotational force like this, you get some resistance just along the in between the slices themselves, and against the surface of the slope. So that's why the force increases as the interslice shear increases. So once again, depending on your project conditions, this may or may not be a suitable choice of shape for you. So if you're expecting little to no sort of shear forces acting perpendicular to, or excuse me, normal to the slope itself, then this may be of use to you. Whereas if you're expecting a significant amount of maybe moment acting on the slope, then once again that'd be another sort of thing to consider. Would make it that would make this shape more effective for you, since it takes moment into account. Okay, and now we have a composite slip surface, which is typically the most widely used type of surface. So once again, the main difference is that both moment and force are affected by interslice shear, specifically because of its shape. So even though it still has the sort of circular shape, As you can see, it also extends to this point beyond the end of the slope here. That's why, if you were to apply some rotational force upon it, you'd still experience some amount of resistance just because of the way the slices are sort of oriented, especially along this piece over here. You'd still have a certain number of forces just sort of acting or resisting the moment. And the same with the force. If you were to apply a force in the normal direction to the slices, you'd experience some resistance. So once again, both your slope, both your moment and your force would be affected by interslice shear. So this is the most accurate, and this is the surface that's utilized by Spencer and the Morgenstern Price methods. So these, to do the calculations for a composite slip surface such as this is lengthy and sort of harder to do, by hand. But once again, if you have the, if you're using one of those programs that we mentioned, and it's really not an issue at all. So that was sort of one of the big breakthroughs of just using numerical modeling in general, is that it made methods such as these much more accessible. Okay, and then let's talk about a block slip surface. So as you can see, instead of a circular shape here, it has these sort of very sharp corners. So something this tends to lead to erroneously high moments and shear forces, and thus erroneously high, factor of safety calculations. So with this, because of these sharp corners and because of the extra resistance that you receive, essentially you're taking a very sort of conservative approach to your LEM analysis, and you're essentially saying that the slope, you're assuming the slope is more sort of stable than it actually is, because the way that slopes fail, they don't really fail in shapes such as these. Although there are certain materials, sort of maybe stiffer materials, materials that crack or break a certain way, where maybe a failure such as this does occur, in which case it would be more accurate. But it's, just an important thing to remember is that block slip surfaces you need to be used with caution, because they're not used as often, because they're not typically sort of the shapes that sort of occur when the slope failure does occur. So just if you ever do use block failure surface or block slip surface, you just need to make sure that it's sort of a reasonable assumption to make that your slope would fail in such a manner. And once again, that really depends first and foremost on the material, as well as the way sort of your forces are oriented on the slope itself. Okay, so now let's just review some application considerations. So an LEM, or the limit equilibrium method, cannot provide stress distribution and displacement. So that's one of its shortcomings. Although it's excellent for sort of efficiently calculating your factor of safety for your slopes, you can't calculate the deformation of the slope itself, as well as how the stress is distributed just along the sort of the soil elements. It is awkward to use for analyzing stability problems, such as the failure of cantilever and retaining walls, in which failure involves deformed wedges. So once again, if you have any type of sort of retaining walls or support structures, it's very difficult to sort of analyze the effect of those support structures. So that's something we'll talk about in greater detail with the strength reduction method of finite element analysis, is that certain, or just structural supports in general are much sort of better analyzed, or more accurately analyzed with that type of method, as opposed to the limit equilibrium method, which is sort of more specialized to just the factor of safety. So unrealistic stresses for slices does not necessarily mean the factor of safety is wrong. So this is something I discussed earlier. So just keep in mind that if you seem to get erroneously high or low forces acting on your slices, just keep in mind that those correspond to certain assumptions that are made for that slip surface, or that for that sort of certain portion of the slope, and it doesn't necessarily mean that those are the actual forces acting on the slope, and it doesn't mean that your factor of safety is wrong. Okay, so yeah, you should not expect the computed stresses to necessarily represent the actual ground stresses. So just to reiterate, actual ground stresses and computed stresses for your slices are two completely different things. So don't be sort of discouraged, or don't worry if you seem to get stresses that are that seem to be kind of high or low. Just as long as your factor of safety is within reason, you should be all right. Okay, and then limit equilibrium is most commonly used in simple solution method, but it can become inadequate if the slope fails by complex mechanisms such as internal deformations. So if there are certain sort of factors that are causing the slope to fail internally, brittle fracture, progressive creep, and then liquefaction of weaker soil layers. So these are all sort of mechanisms that really don't fall within the scope of the limit equilibrium method. These are one of the main sort of things all of these mechanisms have in common is they all take into account a certain amount of deformation, which really needs to be calculated using the finite element analysis, or excuse me, the strength reduction method. So we'll talk more about the strength reduction method in the following section. But the main sort of concept to grasp about the limit equilibrium method is that it's best suited for sort of smaller scale, or not necessarily smaller scale, but simpler projects that don't require sort of complex failure mechanisms to be taken into account, as well as displacements or maybe sort of large support structures. So if you have projects that are more straightforward, that you just need a factor of safety, and it's very simple as far as the materials that are involved, then the limit equilibrium method would be your most effective choice. Okay, so now we'll just have another quiz. Once again, it's 3 questions, and you'll have up to 5 minutes. Okay, so I see that everyone has submitted their quiz. So now let's move forward into Chapter 3. We'll go over the strength reduction method. Okay, so the main sort of theoretical principles of the strength reduction method are as follows. It utilizes the Moore Coulomb shear strength parameters, so parameters such as modulus of elasticity, the Poisson's ratio, the angle of dilation, tensile strength, etc. Those are all used in the strength reduction method. So the main thing to sort of, or the main idea to get out of these parameters is that they all involve calculating the deformation of the displacement of elements as they're put under pressure under certain forces. So that's the main difference. One of the main differences actually between the strength reduction method and the limit equilibrium method is that the limit equilibrium method doesn't take into account these parameters, whereas if you were to run a strength reduction method analysis, you would need these parameters in order to run the analysis effectively. Okay, it involves successive reductions by some factors in the shear strengths of slope materials until failure occurs. So in this sense, the strength reduction method is also an iterative process. Typically, when you use any type of numerical modeling program and the strength reduction method is used, what will happen is the program will increase the sort of level of shear strengths in the slope until it fails or until it doesn't converge. And then based on when that failure occurs, that's how the factor of safety is calculated. So what it does is essentially it takes the slope and it pushes it to its limit or to its breaking point. And once it finds that breaking point, it relates that to your factor of safety. Okay. And then, once again, failure is indicated when the finite element model does not converge to a solution. So anyway, in other words, when the slope is no longer in equilibrium, that's when the model won't converge. And then that's how the factor of safety is calculated when that situation occurs. And then the critical factor at which failure occurs is taken to be the factor of safety. And then depending on the basis of assumption for the failure strain, the shape of the critical section varies, and significant time is required for calculations by finite element analysis. So that's previously was sort of a drawback for the strength reduction method, is that the calculations themselves took much longer to do, and it wasn't really until the prominence of computer programs that the strength reduction method started to be used more frequently. Okay, so another thing to keep in mind is that the modulus of elasticity will greatly affect your failure mode. So as you can see, we have one slope here, and it's the same project, but the only thing that was changed was the modulus of elasticity. So as you can see, this top slope here, the modulus of elasticity was set to a much sort of lower value, and because of that, where the slope deforms, or the slope deforms in a much different way than this bottom one here, where the modulus of elasticity is much higher. So as you can see, there's a significant amount of deformation, not only around the slope itself, but also around, but also behind it, and also extending, well below it. Whereas when the modulus modulus of elasticity is higher, deformation occurs only at the top of the slope here, or this portion here. So that's another important thing to keep in mind, is that with the strength reduction method you can really get a more detailed understanding of not only the factor of safety but also the way your slope will deform, which, depending on the scope of your project, may be something of vital interest to you. So, for example, if you're to be building maybe a structure sort of on top of the slope, or to have anything that needs to be sort of studied for safety or stability, then understanding the way the slope would deform would be sort of essential for you. So the great thing about the strength reduction method is that you not only get your factor of safety, but you also get certain deformations and strains, which could be useful for you if you're to have other sort of variables to take into account other than just the factor of safety. Okay, so these are factors that previously kept the strength reduction method from routine use. So as I read these, just keep in mind that with the aid of numerical modeling programs, all of these factors have sort of been overcome. So that the strength reduction method is starting to be used more frequently now, more regularly. Okay, so lengthy modeling, computation, and results analysis times. So to do the strength reduction method by hand would have been an extremely lengthy process. It would have been, if you're only sort of calculating your factor of safety, then the limited equilibrium method would have been much easier to do by hand, although that in and of itself was a lengthy process as well. But because of numerical modeling programs that have been developed, these modeling times and result analysis times have been greatly expedited. And then the lack of automated tools for performing the successive changes to shear strength. So once again, because of automated tools that have been created now, the changes to shear strength can be modeled sort of instantaneously or much faster than previously possible before. And then a perceived hunger for material input data, which were not collected in routine site investigations, or at least without reasonable accuracy. So that's another thing that sort of kept it back for a while. But now, so with sort of modern engineering data that's available to you, all of the material input data that are needed, such as the modulus elasticity, the Poisson's ratio, those are typically available for engineers to use in their analyses. And then restriction to linear material strength and more Coulomb models. So another great sort of factor of the strength reduction method is that you can account for not only the near material strength, but also nonlinear material behavior to get a more sort of accurate analysis of how your slope will respond to certain strength, to certain stimuli. And then the unproven reliability of shear strength reduction results. So this has been over time. More and more engineers have started to sort of use a shear strength reduction method and compare it to limited equilibrium results, and they've been checking out. So now the shear strength reduction method is starting to get more credibility as it's being used more and as its results are sort of lining up with those that are found through the limited equilibrium method. Okay, so certain analysis considerations. So first, just assume a single Young's modulus and a single Poisson's ratio for the slope materials. So any sort of materials that are corresponding to the slope itself, it's always a good sort of practice to assume just a single Young's modulus and Poisson's ratio for each, just to keep things simple. Assign all materials elastically, perfectly plastic behavior. So you want to assume that materials will deform. That way you can have a more accurate sort of analysis. And then use higher order elements. For a given number of nodes, higher order elements are generally more accurate. So higher order essentially means elements that are sort of more refined or smaller. So you'll see later on when I show you some more sort of images of finite element models for slopes, is that the elements near and around the slopes are very fine or very small. This is just to ensure a high level of detail in those areas, so that you can get a really accurate deformation, or your shear. You can really get accurate sort of results for your shear stress, because that's how the program calculates the factor of safety. So it's just always a good rule of thumb, just in and around the slope area, to use higher order or smaller elements. And then begin with a smaller number of elements, and then refine the model or increase the number of elements once you've obtained a good handle on the slope problem. So if you're still creating, or if you're still sort of in the preliminary stages of your design for your slope, it's a good rule of thumb to use larger elements. So you'll have a smaller number of elements, but the elements themselves will be larger or coarser. This will help you to sort of cut down on the analysis time. So if you have like larger elements, the analysis runs much faster because the analysis is less detailed. But later on, as you're sort of refining your model and you're getting closer to your submission, and you've accounted for all of your design changes, then at that point you can use sort of smaller elements. That way you can get a more detailed analysis. And then check the sensitivity of result to the number of elements. So then once again, see how your results differ depending on how many elements you use, because sometimes the number of elements doesn't really have too much of a difference on your factor of safety or your deformation, whereas there might be some projects that are extremely sensitive to the number of elements. So it's always good to have one analysis case run with a large number of elements and one analysis case run with a maybe smaller number of elements, so that way you can see how it's affecting your results. And then another thing to note is that the deformation parameters, such as Young's modulus, the Poisson's ratio, and the dilation angle, influence the magnitudes of computed deformations. So for example, if you were to have maybe some deformations that seem maybe erroneously high or low, typically it's directly related to the parameters that you entered for the Young's modulus, the Poisson's ratio, and the dilation angle. So it's good to just go back and to check those just to make sure that those have been entered correctly, or if those are sort of within reasonable values. Okay, now let's take a direct comparison to the limit equilibrium method. So as far as the shear strength reduction method is concerned, it can more accurately simulate the behavior of support elements. So for example, if you have tiebacks, maybe any type of retaining walls or sorrel nails or anchors, the shear strength or the shear strength reduction method can more accurately simulate that behavior. And it can more accurately simulate interactions caused by the relative stiffness of slope materials. So once again, the way that sort of the slope materials interact against each other, especially when they're very stiff, it's much more accurately simulated by the strength reduction method. Can indicate deformations at failure. So once again, if deformation is something that you really need to know for your project, then the strength reduction method is something that you would need to use, because a limit equilibrium method can only calculate your factor of safety. It can't calculate deformations. And then it eliminates arbitrary assumptions regarding the inclinations and locations of interslice forces. So once again, with the limit equilibrium method, you're making various assumptions that sort of might lead to maybe values or results that may not be something that you'd want. So in other words, with the strength reduction method, because less assumptions are made, the final results are going to be more optimized or more accurate. Whereas with the limit equilibrium method, because of those assumptions that you make, more conservative results will be given. So typically, with the limit equilibrium method, you'll get maybe factors of safety that are typically higher than what you'd get with the strength reduction method. And then it can automatically monitor the development of failure zones. So maybe if there's a certain portion of the slope that you want to monitor, that is sort of the critical sort of portion of your slope, the strength reduction method can sort of closely monitor that to see how that that zone starts to fail. And for example, if you want to maybe add some structural supports to that zone, you want to design specifically to support that zone, then the strength reduction method would be an adequate tool for you. And then it can be used to design the support of elements in a slope. So for example, tiebacks, retaining walls, sorrel nails. If you're doing the design of those elements in particular, then the strength reduction method would be very adequate to use, because you can get the forces acting in those elements. You can get the reaction of those elements as well as the deformations, none of which you can get through the limit equilibrium method. Okay, and then here's just the listing of the input parameters. As you can see, with the limit equilibrium method, the main sort of soil parameters that you would need are just the unit weight, the cohesion, and the internal friction angle. Whereas with the strength reduction method, you have these three parameters, but also the modulus elasticity, and the Poisson's ratio for deformations, and also the draining condition to calculate effective stresses. So that's another thing to keep in mind, that if you plan to use a strength reduction method, just be prepared to have to make that extra effort to get all these additional parameters for your soil. Okay, and then here is the comparison of two different models. So to the left here is your strength reduction model. So as you can see, as I said earlier, as you get closer to the slope, or just the area of the slope, the elements are much smaller or much finer, because you'd want the analysis to be more detailed along this area, so you can get your deformations and your failures. Whereas as you go farther away from the slope, the elements become larger, because these areas really aren't as of much interest as this area. It's really this area that's going to fail that you need to support for. But anyway, going back to sort of the comparisons of these two models themselves. So as you can see, the strength reduction model is done in finite elements, so you need to create your meshing. Boundary conditions also created, so you have your rollers on the sides here to account for deformations or up and down movement, and then you also have your pins on the bottom here to account for any sort of rotational movement. Whereas with the limit equilibrium model, you don't need to create a mesh set. Essentially, you just have these surfaces here assigned with your material properties, and then you'd have a number of arc failure surfaces. So this one is a composite failure surface, but as you can see, it's a series of sort of arcs here. And what the program will do is it'll take each of these arcs and will create a series of slices for each, and it'll calculate the forces and the factor of safety for each arc, and then it'll find sort of the critical arc or the critical factor of safety, and it'll isolate that. And as far as this grid range here, what the grid range is used for is it's just used to sort of select or to create a series of arcs. So every time I click on one of these dots, it'll correspond to a different arc set. So that's essentially the point of the grid range. Okay, and once again, as you can see, the grid range here in the post-processor and the results mode, this area here is red, which represents sort of the critical area. So here's where your factors of safety would be the lowest. And once again, it'll isolate the grid range, or excuse me, the arc failure surface that corresponds to a point on the grid, and your factor of safety, or minimum factor of safety, will be isolated. So in this case, the factor of safety is about a 2.855. And also, if you double click, you can get your, if you double click on just the slices themselves, you can get the forces acting on each of them if you want to double check. Okay, but with the strength reduction method, aside from just the factor of safety, there are other results to be taken into account as well. So the factor of safety for this project was about a 1.675. But in addition to that, they'd also calculated the displacement, so this is how the slope would sort of deform. Also the pore pressures, so as you can see, as you go further and further sort of near the surface, the pore pressure is higher. The effective stresses, so it takes into account the pore water pressure. Once again, it's highest just along this top ridge of the slope here. And then also the axial stresses of these tiebacks here. So once again, that's another key advantage of the strength reduction method, is that you can design for any sort of structural supports in your slope. So that's just the main thing to keep in mind. And also I want to point out that the factor of safety here is much lower than what was given here for the, because this is the same project, it's modeled with two different, or excuse me, analyzed with two different methods. So the limit equilibrium method, the factor is about 2.285, but here it's about 1.675. So just keep in mind that because this strength reduction method can take into account pore water pressure directly, and other certain factors, you can get factors of safety that are much closer, much more, I guess, realistic. Anyway, so that's just the main sort of thing to remember, is that the strength reduction method is used for sort of higher end analysis, whereas the limit equilibrium method is used for just when your only concern is just the factor of safety. Whereas with the strength reduction method, you get the factor of safety along with several other sort of results that depending on your project may be of interest to you. Okay, so now we'll have one last quiz before we go into our final section. Once again, it's 3 questions, multiple choice. Just select one answer for each question, and you'll have up to 5 minutes. Okay, so now we'll move on to Chapter 4, which will go over specifically how slope stability analysis is used in dam design. So we'll go over seepage analysis and how that's sort of related to seepage slope coupled analysis, and then we'll go over the rapid drawdown effect, and then we'll go over a case study. Okay, so things to remember about seepage analysis. So as you can see, hydraulic pressures, or just the water within the soil itself, tends to have a great effect on the stability of slopes. Just imagine, here's a water table here, but just imagine the water seeping through the soil and flowing down to this river. As it continues to do so, the stability of the slope here will be compromised. And if this pressure becomes high enough and constant enough, or if it constantly keeps flowing and becomes high enough, eventually the slope actually could fail. So now, the reason this is important for embankment design is because whenever you have any type of earth dam, there is a certain amount of seepage that takes place from areas of high water pressure, or your reservoir, to areas of low water pressure, or to the other side of the embankment or the slope. Excuse me, the other side of the embankment or the dam. So as you can see here, the embankment is sloped on both sides, and here's the water table, and as you can see, water will just continually seep to the other side of the dam, thus causing, instability of the slope here in this area. As you can see, as shown by this red line, here's the slip surface. So if this seepage were to become, or to increase to a point where, the slope could fail, then that could lead to sort of, several issues for your dam. So whenever engineers sort of design embankments or dams, they'll always sort of take into account the seepage, and they want to make sure that the seepage won't cause any sort of failure on the dry side of the embankment. So in order to sort of calculate the forces or the seepage that's occurring in this dam, they need to run a seepage analysis. So there are certain things that need to be determined for a seepage analysis. So the main sort of parameter that you need to take into account is the coefficient of permeability. So essentially what the coefficient of permeability is to measure of how fast water can travel through a certain medium, or through a certain soil type in this case. So here, as you see through this table here, we have permeabilities for various soils ranging from very high permeabilities to very low permeabilities. So, for example, gravel has very large pore spaces, or the spaces in between gravel are very large. That way, the water can travel very quickly through it. So it's very good for any type of drainage condition that you have. Whereas as you go into coarse sand or fine sand, the pores, or the areas between each sort of grain of sand, become sort of smaller, and it takes longer for water to seep through there. Until finally you have sort of clay mixtures, or clays just in general, where clays, as I'm sure you know, have very small pores, and it takes a very long time for water to escape through them. Sometimes takes weeks, months for the water to escape through clays when constant pressure is applied to them. So essentially, that's why sort of clay cores are often used for earth embankments, just to sort of stop the seepage through maybe looser soils. Okay, and here are just examples, and I won't go into too much detail about just seepage analysis as far as numerical modeling is concerned. I'll just focus on the results for now. But when you do a seepage analysis, and let's say, for example, this left side here is where the reservoir is located, you'll have several results available to you when you run the seepage analysis through a finite element program. So first you'll have your head. So areas of high water pressure will actually be to the left where the reservoir is, and it'll go transition slowly to low water pressure to where the dry side of the embankment is. You'll have your pore pressure, so naturally, pore pressure is going to be higher where the water is. And then flow velocity, which is very, important. So as you can see, the flow velocity, so water will be flowing from the left side to the right side. And what the program is telling us here is that flow velocity will be at its critical point in this area. So this is where the sort of maximum amount of seepage occurs, which is right here around the slope. And later on, the flow velocity, or the just the forces in general acting upon this slope due to seepage, will be taken into account when doing our slope stability analysis. That way, engineers can determine whether or not the seepage, or the forces that are acting upon the slope due to seepage, would warrant maybe a redesign or any type of structural support. And then naturally the hydraulic gradient. So, obviously this area here would be the sort of critical area as far as hydraulic gradient, because as you can imagine, water sort of takes the fastest route from areas of high water pressure to low water pressure. So water will be, sort of traveling very quickly from this point here to this point over here because it's closest. And once again, there will be, a significant amount of seepage occurring in this area here. So some other things to take into account is you can determine the pore water pressure loads, which are used directly in your slope stability analysis. I'll discuss that shortly. You can determine the groundwater level. So for example, if you want to make sure that the water level doesn't exceed a certain point on this side of the embankment, then with a seepage analysis you can calculate that. You can estimate the flow, the way the water behaves, how it travels, how much water can be expected to seep through the other side. Piping potential, so for example, if you wanted to create any sort of drainage, you could find out where the hydraulic gradient is, you can find out where the water is going to be so that you can drain it. And then as far as advanced analysis, you can consider changes in rainfall. So for example, if it were to rain on this side of or if it were to rain just over a couple of period of days, the water level on the side of the embankment would increase, thus increasing the seepage and the pressure acting on the slope. So those are things that you can take into account with the seepage analysis. And then rapid drawdown, which we'll discuss shortly. Okay, so here we have just some examples of some dams or some earth dams. So the dams are homogeneous, which means the soil material is uniform throughout the dam. So as you can see, here's the sort of flow path that the water takes. And once again, as you can see, this portion here is experiencing a significant amount of seepage. So depending on just the strength of your materials, the level of seepage, the stability of this side of the dam can be compromised. Whereas if you have implemented a drainage blanket, as shown here, the seepage or the flow path changes very significantly to the point where all the water is seeping down into the drain and the water is being safely sort of drained out the other side, while maintaining the stability or the structural integrity of this slope here. So that's why sometimes a clay core is used just to block the seepage or to slow it down, or a drainage blanket or a drainage pipe is included, just to sort of change the direction of the water. So that's one solution that could be created for your dam. Now, coupled analysis. So say, for example, you want to do a coupled analysis just to see if a measure such as a drainage blanket or maybe a clay core would be needed. So we reviewed this in one of our previous lectures, but just as a review, first and foremost, you'd perform your seepage analysis to get your pore water pressures. Then you'd extract your pore water pressures and you'd reflect those into your stress analysis or your slope stability analysis. And so as you can see, the pore pressures would be modeled directly into your pore water pressure, or excuse me, they'd be modeled directly into your slope stability analysis. So here we have an example of a slope stability analysis with a pore water pressure taken into account, and as shown by this blue line here, that's where sort of seepage is occurring. And the factor of safety is about 1.3, whereas when it's modeled without the pore water pressure, the factor of safety is about 2.0875. So as you can see, the effects of pore water pressure tend to sort of weaken the slope considerably. So as we discussed earlier, the minimum factor of safety is usually about a 1.5. So in a case such as this, engineers might look to make some remedial designs to keep the water from seeping over to the other side to that degree. So that's another good thing to do. It's another good practice is to see how the pore water pressures directly affect the stability of your slope. And the good way to compare that is to model it with and without the pore water pressure, as shown below or shown here. Okay, so now let's discuss rapid drawdown effect. So essentially, what rapid drawdown is when the water is drained from a certain reservoir or embankment at a very quick rate, usually over the course of maybe just a couple of hours or maybe even a day. So in studying the effects of rapid drawdown, one of the things to take into account is that the presence of the water is actually helping to stabilize the slope here, because of just the way the water is acting upon the slope. It's sort of keeping it stable. Whereas if this water is taken away, the slope suddenly becomes less stable because it has, it doesn't have that force acting downward upon it. Also, because of the way that the water seeps out of the slope, because of its sort of, that suction, that slope will receive, will suddenly, the factor of safety will, sort of plummet very quickly. And as the water slowly drains out of that slope, it'll regain its strength, very slowly as well. So that will make, these factors are what make rapid drawdowns sort of unique and important to take into account. So there are two ways you could analyze the effects of rapid drawdown. So the first approach is to perform an additional slope stability analysis with an assumed piezometric line after rapid drawdown. In other words, you'd have a before and an after. So before rapid drawdown, here's your water level. You'd calculate the factor of safety by taking into account, just the hydrostatic loading. And here it's about a 2.78. Whereas, you have like an after setting. So here, maybe the reservoir isn't drained completely. The new water level would be here. So you just, analyze the stability of that dam with just the new water level. And here, as you can see, it's a 1.87 because the water isn't stabilizing as it was before. So that's, this is sort of the simplified way of going about doing the analysis. The one thing that you're missing out on, though, is you're missing out upon sort of that critical time before the slope is stabilized. So as I mentioned earlier, when you do a rapid drawdown, because of the way the water just, creates sort of a suction on the slope, the stability of the slope will drop very rapidly until it starts to settle, and then eventually the water will start to drain out through the pores, very slowly over time, and then it'll regain its stability. So if you want to account for that sort of period, you need to do maybe a more detailed analysis. So here we have approach 2, which is a transient or a time-based analysis to consider hydraulic properties of the materials. So as you can see, instead of just taking a before and after, you'd actually, just using your numerical modeling program, you'd be able to create, a series of analyses over a period of time, and it would sort of see, you'd analyze how that how the slope stability would be affected as the water level changes very gradually. So here is just, a series of piezometric lines, very simplified sort of picture though. And as you can see, the factor of safety starts off at 2.6, but then because of rapid drawdown, this factor of safety versus time, by the way. So the factor of safety starts off at about 2.6, but within, just a couple of seconds, it plummets down to about, maybe 0.8, I think, or 0.7. So as you can see, that's a very significant drop. Then later on, after the, water starts to drain from the soil, the slope will start to regain some of its stability, although it won't be as strong as it previously was before. So as you can see, I believe this is over maybe a couple of days. The slope will regain its stability over time. So if you were simply to do a before and after in the previous approach, you'd get this factor of safety and this factor of safety. But it's really important to remember that in between that time, the factor of safety could drop well below your final factor of safety here. So, for example, the approach mentioned in the approach 1 might not be effective since, your slope could actually fail around this area here. So if you want to make sure that you're, if you have like a certain slope where you feel like the factor of safety could drop well below a minimum factor of safety, then it would be, very beneficial to do a analysis type such as this, just so you can, make sure. If that were the case, obviously you would need to do some remedial changes, maybe change the dimensions of the slope or add something to ensure that the slope doesn't fail when rapid drawdown does occur. So once again, that's the main sort of difference between approach 1 and approach 2. Is that approach 1 is simply a before and after, whereas approach 2 considers everything that happens in between. And just the main thing to keep in mind is that the factor of safety when rapid drawdown happens is it plummets very quickly, well below your final factor of safety after your slope begins to stabilize after a while. So that's one of the main things to keep in mind, is that for projects where you feel that the slope might fail during rapid drawdown, where the factor of safety might drop to a very low point, a point that would need to ultimately be changed for future design purposes, then approach 2 would be useful for you. Okay, so now just to wrap up, I'll go over just a case study. So for those of you who attended the first session, this case study should be very familiar. It's the Carsington Dam in England. One of the main things, or the things to keep in mind, is that the initial slip, or the initial factor of safety, was calculated to be about 1.4 by the limit equilibrium method. But the value was reduced to 1.2 by the presence of the pre-existing shear surfaces, and finally it was reduced to 1.0, and eventually the dam did fail. So what was the cause of these pre-existing shear surfaces? The cause of these shear surfaces was formed by something called periglacial solifluction in the natural ground forming the dam foundation. So what periglacial solifluction is, it's a result of it's a result of water in the soil being periodically frozen and unfrozen. So this dam was built in sort of a seasonal area. So obviously it had a winter and it had a summer, and over those periods of time when the water in the pores of the dam was frozen, it created additional shear forces acting in the dam. So as you can imagine, when water freezes, it expands. So just imagine all of the water in this dam expanding over the course of a winter. So that'll cause some breakage or some shear forces within the dam. And then just imagine all of that water melting during the spring and maybe seeping out. Those shear forces are going to be increased. And just imagine this happening periodically over maybe a couple of years or even over a couple of months. That's going to eventually sort of cause so much shear within the dam that it failed. So why is this significant? The reason this is significant is because engineers realized that by using finite element analysis, the mechanism of failure and the initial propagation of the shear zone could be captured. So in other words, just through doing a seepage analysis, through the numerical modeling or through finite element analysis, the engineers could have calculated or could have accounted for periglacial solifluction or just any type of sort of seepage going through the dam. So this was a big sort of breakthrough project for finite element analysis in general. They saw that it was something very useful and actually something very necessary for projects such as these. So that's why this particular case study is so important, because seepage analysis and slope stability analysis are very linked when it comes to dams and embankments. So that's just one thing to keep in mind, is that when seepage analysis is used, coupled analysis with either the limit equilibrium method or the shear strength reduction method, the shear strength method, then you can get results that are more accurate and that safely take into consideration pore water pressures or changes in pore water pressure. So that's just another important thing to touch upon, and this is just a very good practical application of how finite element analysis could have been used. So this is just one of many projects that really sort of brought finite element analysis to the forefront in terms of engineering. Okay, so this concludes session 7. Next week's session will be next week on Wednesday, the same time. It'll be the final session of this series, and we'll go over the numerical modeling demonstrations of fundamental finite element analysis concepts. My colleague Arun will be hosting it. If you have any questions at all about the session, feel free to give me a call or to send me an email. I'm open to suggestions or any questions. Feel free to contact me. Thank you once again for your time. I appreciate your attendance, and we look forward to meeting up with you again next week.